So today, I want to talk about the so-called difference equation, how we solve a difference equation. In particular, we want to talk about the linear difference equation with constant coefficients. Okay. For example, we have some un plus k plus alpha k minus 1, un plus k minus 1 plus alpha k minus 2, un plus k minus 2. Let's see. Yep. Plus all the way alpha 0 un is equal to something. Right, equal to something. This kind of equation shows up. Let's say if you so e.g. for the forward Euler we just explained, we're going to get this un plus 1 is equal to, I'm using subscript now for this explanation of this tool. All right, and also maybe for the Adams method, right? You have un plus 1. You have un plus 1 plus some un, right? Alpha 0 maybe, plus alpha 1 un minus 1 all the way to alpha p un minus p is equal to something, right? You need to solve. So let's first look into the so-called homogeneous case. The homogeneous case, i.e., the right-hand side is equal to 0, right? The phi is equal to 0. The phi. And the tool here is that is also so-called characteristic polynomial. This is in one of the books as well, right? By having, let's say we look at the star, right? That equation, there's a corresponding polynomial which is r to the k plus alpha k minus 1 r to the k minus 1 plus all the way to r alpha 1 r plus alpha 0. Okay. Alpha 0. And then we solve for the zeros of that. Solve for alpha and the roots of that polynomial. We get alpha r1, r2, rk. Okay, rk. Okay. All right. Because that's what it says, right? If your phi is 0, you have that, and then if you think about it, then we have a solution already for example, the solution, my u m plus I is equal to r j to the i's power for any j is a solution. It's a dirty trick. Suppose you get so for any j here, j is 1, 2, all the way to that k, right? So I will write down what I just said. Why is that a solution? Because in that case, we get rj to the k, right? Plus alpha k minus 1 rj to the k minus 1. This corresponds to um plus k. This corresponds to um plus k minus 1 plus alpha k minus 2 rj k minus 2. In the end, alpha 1 rj to the 1 plus alpha 0, and those are the corresponding values. Here is um plus k minus 2. Here is un plus 1, right? Here is un. Okay, and this is of course 0 because rj is a solution. It's a 0, right? It's a 0. Think about j. One j is 1, right? Any j, fixed j. So this is so-called fundamental solution. A fundamental solution to the difference equation. In fact, you already see that so many more, right? In fact, the um plus I, right? We plus I is equal to alpha j to any m plus I, right? We can multiply, basically, we multiply that fundamental solution by rj to the m. That's simply multiply the whole thing outside by rj to the m. 0, we multiply by that, it's of course 0. Is also a solution to that equation, right? For any m. For any m. Right? So what do we have is that we have alpha, if e.g. if j is 1, we have r1 to the m plus k plus alpha k minus 1 r1 to the m plus k minus 1, and so on and so forth, which we just factor out r1 to the m. We have r1 to the k plus alpha k minus 1 r1 to the k minus 1, which is r1 to the m times 0, which is 0. Okay, which is 0. What's next is a discussion into two categories. The first one is that if all those roots, you get your characteristic polynomial. If all those roots, all right, the k roots, if they are all simple roots of that characteristic polynomial pi r, then all solutions of that difference equation can be written as un is equal to some coefficient. I'm going to use, because we have alpha already, we're going to use gamma 1 r1 to the n plus gamma 2 r2 to the n plus gamma k rk to the n to that. This is true for any n. So it's a linear combination of those roots to the corresponding power. You check this. This is a homework, right? It's basically what we did above. Different combinations of what we did above. So simple root is those with multiplicity 1, right? Simple root are those with multiplicity 1. For example, if we have x times x minus 1 cubed, then there are two solutions, 0 and 1. And 0 is simple, 1 is not. Right? 1 is not, because 1 has multiplicity 3. Okay, 3. Multiplicity again is defined to be, you plug in 1, you get 0. You plug in 1 into the derivative, you also get 0. You plug in 1 into its second derivative, you also get 0. Right? You plug in 0, you get 0. But if you plug in 0 into the derivative, it's not 0 anymore. So if there are roots that are not simple, let's say instead of R1 to RK, if you list all the different roots, you only have up to K star, K delta. Let's say we have R1 to R K delta, and they have multiplicity M1 all the way to M K delta. If they happen to be, if one of them happen to be simple, then just M is equal to 1, because the M is 1. Okay. In that case, then the solution, the UN, then UN just uses, instead of use R1, those simple solutions to the power n. Here you just use again that Rj to the any n, right? J is 1 to K delta, and n R J to the n. J is from 1 to K delta, and n to that multiplicity minus 1 R J to the n. J is from 1 to K delta. Okay, which is, I mean, if we write on the solution, is kind of confusing. But basically, instead of this, which is just first group, when they have higher multiplicity, usually you reach them. It's a linear combination of more things. i.e., let's write them down anyway. So the solution then is equal to, you go through all the roots of the characteristic polynomial. For each of them, you go through its multiplicity, okay, from 0 to mk tilde minus 1, and you're going to get a coefficient gamma jl, and you have this n to the l rj to the n. I'm going to give you two examples, okay. The first one is that if I have un plus 2 minus un is equal to 0, right? The homogeneous case. From the scheme, we're not going to get 0, but to going from 0 to non-zero, the standard technique. Anybody remember that from ODE? Like you can solve. So for the inhomogeneous case, for the inhomogeneous, which is if that right hand side is not 0, is not identical to 0, then we use a so-called, I think, variation of parameters. So let's look at this example. Here, of course, then we're given is a two-step method. We're given u0, u1. Okay. It's a two-step method. And then we know the pi r is equal to, from here, is r squared minus 1. So the solution is -1 and 1, right? -1 and 1. Solution -1 and 1, right? And by our number 4 above, once you get the solutions, then our un, so the un is nothing but a gamma 1, -1 to the n, plus gamma 2, 1 to the n. Right, 1 to the n. And we are given u0, u1, so in particular, u0 is those would help us solve for gamma 1, gamma 2. Okay, because if n is 0, so you have what's that? Gamma 1 plus gamma 2, right? When n is 0. When n is 1, you're going to get gamma 2 minus gamma 1. So which basically says that you can solve for those constants. Okay, constants. Like when you solve ODE, you have constant. You use the initial condition to solve for the constant. So here, I get my gamma 1 is then u0 minus u1 divided by 2, right? And my gamma 2 is u0 plus u1 divided by 2. And my un now is then equal to 1/2 u0 minus u1, -1 to the n, plus u0 plus u1. All right. If the plug in a second example, and maybe talk about some technique which you might have forgotten. So if we have, let's say, just anyone, un plus 3, minus 2, un plus 2, minus 7, un plus 1, minus 4, un is equal to 0, right? And then we easily have the characteristic polynomial is r cubed minus 2r squared minus 7r minus 4. All right, minus 4. Okay. The -1 is solution, then we know this is r plus 1, right? If -1 is solution, then r plus 1 is a factor. Okay, it's a factor. And then we just need to continue solving, we just need to figure that out. one way to figure that out is to do a division, right? A long division. A long division, that's something nice to be able to do. What's that? R cubed minus 2r squared plus 7r minus 4 divided by r plus 1. You do r squared, so it's r cubed plus r squared. Here is what's that? Negative 3r squared minus 7r. So you're going to get minus, is it right? Minus 3r, yes sir. Minus 3r. So we have minus 3r squared minus 3r is minus 4r minus 4. That's nice. So that's minus 4, you get 0, right? So here is r squared minus 3r minus 4. That's a quadratic, which we know how to handle. Okay? So this is r plus 1 times, here is r plus 1, r minus 4, right? The minus 4. R minus 4. Okay? So in particular here, that's r plus 1 squared times r minus 4. We know negative 1, the multiplicity, the r, and the corresponding m. Here is negative 1 of 4. This m is 2, that m is 1. Right? That m is 1. So our k delta is 2. The number of distinct roots is 2. Right? It's 2. And what we had above is simply that, well, we can use negative 1 to the n and then 4 to the n, right? But because negative 1 has multiplicity 2, you need to consider n times negative 1 to the n as well. Use those 3 because negative 1 has higher multiplicity. And then take a linear combination, right? With any coefficient would be a solution. So the un would be a gamma 1 negative 1 to the n plus gamma 2 4 to the n plus gamma 3 n negative 1 to the n. Okay? And negative 1 to the n. That's all the difference. And of course, this is a 4-step method, right? A 3-step method. So we're given 3 initial conditions. If the 1 step is you're given 1 condition, you 0. The 2 step you have to give 2, like the one above, you 0, you 1. So what that means is that if we're given u0, u1, u2, or maybe you are giving u0, but we use other schemes to generate u1, u2. Once we have those, you solve gamma 1 for gamma 1, gamma 2, gamma 3, right? It's basically a 3x3 system. You solve a 3x3 system for gamma 1, gamma 2, gamma 3. Okay? Gamma 1, gamma 2, gamma 3. So basically, this is just a tool